Okay, section 5.5 is systems of inequalities. So just like we did before, it's a system. So we're going to have multiple inequalities graphed on the same graph. In order to kind of get the idea of what we're going to be doing here, we're going to go ahead and graph just one linear inequality to kind of give us the idea of what we're looking at. So if we were to have a graph of some kind, and we were to graph a linear inequality, something like, something where you've got a greater than or less than, or greater than or equal to, less than or equal to, and you graph the line like this. Whatever this line is, maybe we're going to say that, I'm just going to make something up. Maybe this is x plus y is greater than 2. X plus y is greater than or equal to 2. We'll say that. The general idea is this line right here separates our plane, which is the entire xy coordinate axis, into two sections. You've got this section up here, all of this space up here, that technically goes on infinitely up and to the right. And then we've got this section down here, which is everything which goes down and to the left from that inequality. All of the stuff up and to the right and all of the stuff down and to the left are what are called half planes. So the part in yellow and the part in green create what they call a half plane. So when you take a line and you put the line through your graph, it actually cuts the plane in half. Now technically, because planes are infinite, they go on forever, even though there's only certain parts of it that we can see that we graph here. The planes go on forever, so you're like, how can I cut something which is infinite in half? Well, that's just what they call it. It's not technically cutting it in half, but these pieces right here, this is called a half plane. And then on the other side would be the other half plane. And the idea is we want to figure out, by plugging values in, which side, which half plane is true. Which part of this is actually our solution, because every point in the yellow or every point within the green section is going to be a true statement. We just got to figure out which half it is and then figure out how we're going to denote that. Well, we're going to denote it by actually shading in the correct half. Now I went ahead and shaded both halves here, so that doesn't really help us. But that's the general idea behind what we're doing. And then when we have a system of inequalities, then we're going to have multiple of these graphs put on the same graph. So ultimately, the biggest thing that we're going to have to be able to do here is we're going to have to be able to recognize the graphs and be able to sketch them, because I think that's really going to help us to be able to figure out what's going on with these graphs. So that's what we're going to do when we come back, and we're going to do a couple examples. Okay, for our first example, we're going to just graph a linear inequality. So kind of like what we just talked about. And show how this works. So we've got the equation, or excuse me, the inequality, 2x minus 3y is greater than or equal to 6. And what we want is we want the solution set to that. And now, because it's an inequality, there's going to be lots and lots. There's actually going to be an infinite number of points here that satisfy this. There's not going to be just one or two solutions. There's going to be an infinite number. So let's see how we figure it out. First of all, we need to be able to graph this. Now you could do this in one of two ways. You could solve this inequality for y and make it a y equals, and make it like a y equals mx plus b type form and graph it that way. In this case, because of the way it's set up with the x's and y's on the left side and then the constant on the right side, we can probably use the intercepts a little bit easier. Remember that the idea was, if I was to simply cover up the 3y, or the negative 3y, so basically, and I'm going to erase this in a second, if we eliminate that right there, all you have left is 2x is greater than or equal to 6. Well, you would solve that for x by dividing by 2. So if you divide both sides by 2, you would get that x equals 3. So on our graph, I have a value here of x equals 3. That's your intercept. Okay, now instead, let's say that instead of that, we wanted to find the y-intercept. Well, I would do the same general idea. I would eliminate the x part, and then I would solve what's left over for y. So if I was to divide both sides by that -3, now keep in mind that is a negative out in front of the 3 there. So if you divide both sides by -3, you would get y equals -2. Don't worry about flipping the inequality sign. We're just trying to find what y would equal on the axis. So if y equals -2, here's -2. And notice I didn't have to write every single tick mark. I only needed enough here to draw the line. So now I'm going to go ahead and erase those cross outs. We only did that part there to visualize what we're solving for. That gives me 2 dots. All I need is the 2 points on the line to draw the line. So let's go ahead and sketch the line that goes through those 2 points. Whoops. Hopefully I can undo that. Okay, good. I accidentally erased the whole thing there. So let's go ahead and put our line through those 2 points. There we go, something like that. So what we've created is we've created 2 half planes. We've created the part which is basically to the up and left of that red line, and then the part which is down and right of that red line. So what we have to do is we have to take a test point. And I'm going to take an easy point here to test. The easiest thing to do, if you can test it, is to test the origin. So if your lines do not go through the origin, that's a very easy point to test because that's the point 0, 0. So what I'm going to do is I'm going to plug 0 into both x and y because that's the point. So this will be our test point, 0, 0. I'm going to plug 0 in for x, 0 in for y, and see if we get a true or false statement. Well, 2 times 0 is 0, 3 times 0 is 0, so 0 minus 0 is 0. So what that does is it gives me the statement 0 is greater than or equal to 6. And what we have to ask ourselves, is that true? Well, 0 is definitely not greater than or equal to 6. So this is a false statement. And what that tells me is, because this statement, the point right here is false, every point over here is also false. All of those points are false. So those are not part of our solution. So I'm going to go ahead and get rid of as many of those as I can here. But all of those points over there are false, which tells me that the points on the other side of the red line have to be the true part. So what we've done by figuring out that 0, 0 is false is figured out the other side of the line is true. So everything over here is going to work, and this is how we determine the domain. So this is actually what you do. You show this as your shaded section. Everything on that side of the line is going to be true. That is your solution to the system, to that linear inequality. There really is no way to write like a set of points that include all of that. So you just have to show it by the graph. Okay, for our second example, we're going to do the linear inequality y is greater than -2/3 x. Now this one is different than the previous one in the fact that the x's and y's are not both on the same side. And as a matter of fact, this one is already written in y equals mx plus b form, where the m, which is your slope, is -2/3, and the b, which it's not there. And since the b is not there, that means b is 0. It means this thing goes through the y-intercept at 0. So let's go ahead and sketch it. So the y-intercept is 0. And then I can use my slope of -2/3 to find a second point. Well, -2/3 means that I'm going to go down 2 and right 3. So I'm going to go down 2 and right 3. So my second point should be right about there. Now there's one difference in this one that we didn't talk about before, or 2 differences actually. One is that there's no equal to sign underneath of the inequality symbol. So this is just a greater than. When we draw something that has just a greater than or just a less than and there's no equal to symbol, we actually have to dash our line. And the reason for that is because everything that's on the line is not going to be included. So when we draw this, it's going to be a dashed line that goes through there. And that only happens when there's no equal to symbol underneath of your inequality. So we will dash the line because it's not going to be included in our solution set. The second thing is, what I said on the last problem was, if you can test the origin, and that's going to make it easy to figure out which side of the line we have to shade. So here we're either going to shade the up and right part or the down and left part, because that's how it's separated. The problem is the origin is on that line. It's on our boundary line. We can't test any point on the boundary line because that doesn't help. We need to figure out what's going on the other side of the line, not specifically on the line. So we can take any other point that we want to. Pick easy numbers to deal with. That's what I would do. So we could either test this point right here, which is the point 1, 0. You could test the point right here, which would be the point 0, 1. You could test the point right here, which would be 1, 1. Any of those are really easy to deal with. I'm going to test the point 1, 0 just to see. So my test point is going to be the point 1, 0. But again, anything on either side of the line you can test. Again, what we're looking for is if it's true, we'll shade that side. If it's false, we'll shade the other side. So let's go ahead and see what we got. If we test the point 1, 0, I'm going to plug 1 in for x and 0 in for y. So that would give me the statement 0 is less than negative 2/3. Is greater than negative 2/3 times 1. So what we get is 0 is greater than negative 2/3. And the question is 0 greater than negative 2/3? Yes, it is. 0 is bigger than any negative number. So this is a true statement. And that's good. That tells us that because this point right here is true, every point on the same side of our boundary line on there is also true, so we will shade the true section. So up here, let's do this in green, we are going to shade this entire section right here. All of this is true. All right, I did not mean to shade outside of the, there we go. All of that, whoops, I'm erasing too much. There we go. All of that is true. So there is our solution to that linear inequality. All right, for our third example, and this will be the last of the just solely linear inequalities we do, these are two linear inequalities that really don't require test points. And you can certainly use test points, but there's really two types that you don't really need a test point for. So let's say that we have the first one might be y is less than or equal to negative 3. Well, if y is less than or equal to negative 3, first of all, that's the horizontal line that goes through negative 3 for y. And it does have an equal sign, so it's going to be a solid line. Excuse me, and if you think about it, where is y less than or equal to negative 3? Well, y is going to be less than negative 3. It's going to be below negative 3. So we don't really need to do any testing. We pretty much should know that everything below this line is going to get shaded because that's where y is less than negative 3. So if you're given a horizontal line like that, you just have to know, okay, is it greater than the line or less than the line, above or below? It should be relatively intuitive to do that. And then we also have the example that x is greater than 2. So again, we're going to go to where x is 2, which is right about here. And we're going to draw a vertical line right through that because x has to be greater than 2. Now remember that there's no equal to symbol underneath of that one, so it's going to be a dashed line through 2. And then you just have to ask yourself, okay, if x is greater than 2, is it to the right of 2 or is it to the left of 2? Okay, if you want it to be greater than 2, that means it's got to be bigger than 2. So it should be everything to the right of x equals 2. Again, no real need to actually pick a point to test. With a vertical or horizontal line, those should be relatively intuitive.